Okay, sorry. I have to repeat. So thank you everybody for the introduction. This work is concerning about an active smart walker. Is a project we've developed in our robotic group in the University of Catania in Italy. Okay, smart walker. Smart walker are some robotic assistive devices, particularly useful for the elderly. The system helps the user in locomotion and with respect to the classical walker, reduce the risk of fall. This work in particular presents a prototype of an active smart walker featuring obstacle avoidance and autonomous navigation capabilities. The system can plan and move in a known environment, adapting its behavior according to the presence of the user. The proposed solution has been widely tested in its different operating modes in a real setting. Just briefly, because the previous presentation also introduced the problem. The problem is of aging population. The proportion of elderly people in the society is constantly growing. So it becomes really important to develop assistive system to allow a better integration in the society of elderly people in their daily activity. So we have the technology that can help the so-called ambient assisted living. The European Commission has specific program for ambient assisted living, and also ISO has developed a standard with the guideline for protective measure and information for use of personal care robots. In particular, we are investigating about walker, because one of the important activity that is compromised by age or by some disability is locomotion. As a consequence, an important function of several devices is to guarantee mobility in autonomy of the user. Walkers are important devices. They contain physical support and stabilizing effect for those persons with reduced mobility and balance problems. This device allows also to perform rehabilitation exercise, and in most cases are more useful and best accepted with respect to wheelchair. There are many assistive locomotion systems, wheelchair, special electrical vehicles, and also augmentative systems like mobility train devices, self-porter, orthosis, exoskeleton, and external devices where the walkers belongs. However, walker can have some problem. Several studies report that the adoption of walker in many situations does not decrease the probability of falls of the user. Walkers sometimes can bump or become entangled into obstacles or tumble into steps or stairs, and as a consequence become the main cause of falls. So it is important to develop smart walker that can avoid obstacles, that can help with respect to passive walker, the user in their operation. The conventional walkers are standard walker or wheeled walkers. And then we have the smart walker. The smart walker can help in different functions. For example, the physical support, the sensorial assistance, the cognitive assistance, health monitoring, and advanced human-machine interface. There are several classifications of smart walker in the literature, and many papers has shown different devices of smart walker. In a previous work, we developed an integration of a commercial walker or some intelligent device for obstacle avoidance. This work in particular was also presented in a previous Clover conference. In particular, we developed a simple system that with some laser sensor, time of flight sensor, and 2 brakes could guide the user to avoid obstacle or to avoid also steps. And this was very cheap and also very useful and intuitive for the user. In this work, we are proposing an active prototype. We have active locomotion in this case, so we have motor in the wheels, but we have also the possibility of the user detection by using a LiDAR, and we have also the possibility to have autonomous navigation. In particular, we have some drive wheels with brushless DC motor drive, DC motor drive board, an RP LiDAR 2D laser scanner that can perform 360-degree scan, and as a main computer system, Raspberry Pi. We have the interface between the main computer and all the hardware, and we have also the possibility to interface with an external computer for monitoring or for the control of the autonomous navigation. As regards the software architecture, we have used Linux, and we implemented all the system in ROS, so we can use modular architecture, because ROS, with its open source possibility and its modularity, allow also to have a lot of libraries that we can use in the community of ROS, and we can develop many navigation environments. In particular, the smart worker is characterized by two types of behavior: the work with the user and the autonomous navigation. They have to coexist to allow the user to move in the environment without too much effort in pushing the worker, or move in the environment while avoiding obstacles, or ask the worker of teaching him or her. The worker locates itself in the environment and is able to reach the goal position by independently planning the path to do, and at the same time avoiding potential obstacles along the path. This is the architecture in the two modality: the working without the user in autonomous navigation and the work with the user. In the work with the user, we implemented some algorithm to detect the presence of the user by using the laser scanner. The laser scanner performs an average of the scan of the leg of the user, so it detects an average distance of the user, and with respect to the distance of the user, is capable to detect if the presence of the user and the distance of the user, and can control with a simple control law the forward velocity in order to anticipate the motion of the user. As regards the autonomous navigation, we implemented the localization algorithm with adaptive Monte Carlo localization and Dijkstra algorithm and dynamic window approach as regards the navigation when we need to implement autonomous navigation. So in this case, we have the possibility to detect obstacles, dynamic obstacles, and we can also reconstruct the map of the environment in order to detect the presence of static, of dynamic obstacle. We can also implement SLAM algorithm to reconstruct the environment. So the autonomous navigation system, it can also be used to control the system when the user is not present, to go for autonomous recharging or for reaching the user when he asks. So we have the possibility to work with the user or work without the user as a mobile robot. Finally, I want to show you a short video with some demonstration. First, in the assistive mode, when the user is detected, the system can anticipate the motion and can move with the user. So the user can decide to stop and the system stop. The user can decide to come back, and the system works independently from the fact that the user is supported by the worker or not. And we have also the obstacle avoidance system. So the system can move. Or we have the adaptive navigation control, where the system can move, can also map the environment, reconstruct the environment, and can also move autonomously in the environment, avoiding obstacle, or reconstructing a map of the environment. When the user come back, the system the worker recognize the user and can help in avoiding obstacle. As I told before, we also implemented the navigation and obstacle avoidance, and also map reconstruction by using algorithms in the ROS environment. And the system is enough robust in its locomotion. Okay, so to conclude my presentation, this work is aimed at improving the daily life of elderly people or patients in the rehabilitation phase that have physical difficulty to maintain equilibrium while walking. The smart walker can operate either in assistive semi-autonomous mode or in a fully autonomous mode, switching to the appropriate mode by detecting the user presence. When in assistive mode, the walker moves at a proper speed, taking into account the distance from the user while ensuring a safe walk through obstacle avoidance. As a future development, we plan to include a force sensor. Here we have a picture of the new system on the handles of the walker in order to sense when the user is holding them. In this manner, it would be possible to perform posture monitoring by checking the distance of the legs with respect to the ground projection of hands position, thus being able to correct the distance between the user and the walker itself, and even to prevent potential falls. Thank you very much.
Thank you, Giovanni, for a nice presentation. Is there any question? We have time for at least one question. Okay, we have two. Yes, sir.
Thank you for your nice presentation. So you tried only with LC young people, or you already tried with someone with motor impairments?
For this prototype, actually, we just made a prototype that was tested with young people, but we have some interaction with the hospital, and we are planning some test campaign also with older people, but not yet.
Could you just please elaborate a bit more how you do? I mean, you detect the user is there. What if the user does not follow your suggestion, but still, I mean, it will stop, and so if the walk just turns and the user does not turn, it will, while avoiding the obstacle, what will do? Will stop.
Okay, I understand there are many different situations that should be planned in advance. In any case, it depends from the kind of the user. The actual system need the user interact in some way with the system. So if the system is going away, the user need to reach or to control in order to get again the control of the system. So the system is going forward, asking the user to follow him, but if the user doesn't want, the worker will recognize the user is no more there, and we can, according to the different user, the different situation, plan different recovering strategies, obviously.
And have you considered how you will include the motion intentions of the user, so that it is the user that controls or at least how you combine the motion intentions?
In some way, this work was the beginning of starting to predict the user intention by understanding the distance and the position, but you know that a good control to understand very well the user intention is not an easy task. So this was a first step toward this function.
Thank you. Thank you.
So can we go for the next?
Thank you. And usually the elderly tend to fall down by the small step or slope, I think. So your system can detect the small step or slope using your 2D laser rangefinder?
Actually, this can detect step,
Yeah.
but the previous system we put, we had also a time of flight sensor looking down that can also detect slopes. This was not integrated in the system, but it's not difficult also to integrate this kind of to detect steps.
Okay, thank you very much.
Thank you. We have one more question from the online.
Oh, okay.
I hope you can
Thank you.
see it
hello.
from the
Sorry.
comments.
Sorry.
Yes.
Hello, Giovanni. Hi, it's Clive Lachlan here, editor of the Industrial.
Oh, hi, Clive.
Hi there. Hi, well done. Really enjoyed the presentation and your project, please. I think it's very, very practical. Have you discussed possibly the sort of commercial exploitation of the work, or do you think it's at too early a stage? I'm just wondering if you could link up with a company that could produce these for you.
Actually, we have some interaction with some hospital, and also we got some interest of some company for investigating the possibility of exploiting this kind of system, both the previous one and this one. Our objective was to adopt very cheap hardware as regard the computing, but also the motor, also the sensor. We use a very simple LiDAR. Is the same LiDAR is adopted on vacuum cleaner, for example, that is very cheap, not expensive like Shunk or Okuyo laser scanner. Also the computing was a Raspberry Pi. The motor are similar motor to those used in overboard toys. So very simple hardware. So we can think about commercialization of the system also with a low price.
Yeah,
we have not yet a real interest of some company, but we have some contact up to now.
I think it's very good. I think it's much better to come up with a simple system that will do a job rather than a complicated and expensive one. So well done.
Thank you, Clive.
So thank you again, Giovanni, for your
Thank
nice
you again.
presentation.